This is a photo of a plate with a large pile of eggs in the foreground and 6 slices of toast in the background. There is a small dish of red jam sitting near the toast on the plate, figure 10. 1. If you want to test a claim that involves two groups, the types of breakfasts eaten east and west of the Mississippi River, you can use a slightly different technique when conducting a hypothesis test. Credit. Modification of work, scrambled egg, toast, and homemade berry jam, no added sugar for breakfast by Chloe Lim/Flickr. CC by 2 studies often compare two groups. For example, researchers are interested in the effect aspirin has in preventing heart attacks. Over the last few years, newspapers and magazines have reported various aspirin studies involving two groups. Typically, one group is given aspirin and the other group is given a placebo. Then, the heart attack rate is studied over several years. There are other situations that deal with the comparison of two groups. For example, studies compare various diet and exercise programs. Politicians compare the proportion of individuals from different income brackets who might vote for them. Students are interested in whether SAT or GRE preparatory courses really help raise their scores. Many business applications require comparing two groups. It may be the investment returns of two different investment strategies or the differences in production efficiency of different management styles. To compare two means or two proportions, you work with two groups. The groups are classified either as independent or matched pairs. Independent groups consist of two samples that are independent. That is, sample values selected from one population are not related in any way to sample values selected from the other population. Matched pairs consist of two samples that are dependent. The parameter tested using matched pairs is the population mean. The parameters tested using independent groups are either population means or population proportions of each group. The comparison of two independent population means is very common and provides a way to test the hypothesis that the two groups differ from each other. Is the night shift less productive than the day shift? Are the rates of return from fixed asset investments different from those from common stock investments, and so on? An observed difference between two sample means depends on both the means and the sample standard deviations. Very different means can occur by chance if there is great variation among the individual samples. The test statistic will have to account for this fact. The test comparing two independent population means with unknown and possibly unequal population standard deviations is called the Aspin-Welch t-test. The degrees of freedom formula we will see later was developed by Aspin-Welch. When we developed the hypothesis test for the mean and proportions, we began with the central limit theorem. We recognized that a sample mean came from a distribution of sample means, and sample proportions came from the sampling distribution of sample proportions. This made our sample parameters, the sample means and sample proportions, into random variables. It was important for us to know the distribution that these random variables came from. The central limit theorem gave us the answer, the normal distribution. Our z and t statistics came from this theorem. This provided us with the solution to our question of how to measure the probability that a sample mean came from a distribution with a particular hypothesized value of the mean or proportion. In both cases, that was the question. What is the probability that the mean or proportion from our sample data came from a population distribution with the hypothesized value we are interested in? Now we are interested in whether or not two samples have the same mean. Our question has not changed. Do these two samples come from the same population distribution? To approach this problem, we create a new random variable. We recognize that we have two sample means, one from each set of data, and thus we have two random variables coming from two unknown distributions. To solve the problem, we create a new random variable, the difference between the sample means. This new random variable also has a distribution, and again, the central limit theorem tells us that this new distribution is normally distributed, regardless of the underlying distributions of the original data. A graph may help to understand this concept. Figure 10. Two pictured are two distributions of data, x1 and x2, with unknown means and standard deviations. The second panel shows the sampling distribution of the newly created random variable, x1 minus x2. This distribution is the theoretical distribution of many sample means from population 1 minus sample means from population 2. The central limit theorem tells us that this theoretical sampling distribution of differences in sample means is normally distributed, regardless of the distribution of the actual population data shown in the top panel. Because the sampling distribution is normally distributed, we can develop a standardizing formula and calculate probabilities from the standard normal distribution in the bottom panel, the z distribution. We have seen this same analysis before in the central limit theorem. Figure 7.2. The central limit theorem, as before, provides us with the standard deviation of the sampling distribution. and further that the expected value of the mean of the distribution of differences in sample means is equal to the differences in the population means. Mathematically, this can be stated. Letter 1D438, micro x1 minus micro x2 equals micro 1 minus micro 2 because we do not know the population standard deviations. We estimate them using the two sample standard deviations from our independent samples. For the hypothesis test, we calculate the estimated standard deviation or standard error of the difference in sample means, x1, x2. The standard error is square root letter 1d460 1 2 and 1 plus letter 1d460 2 2 and 2. We remember that substituting the sample variance for the population variance when we did not have the population variance was the technique we used when building the confidence interval and the test statistic for the test of hypothesis for a single mean back in confidence intervals and hypothesis testing with one sample. The test statistic t-score is calculated as follows. Letter 1d461 letter 1d450 equals x1, x2 letter 1d6ff0 square root, letter 1d460 1 2 and 1 plus, letter 1d460 2 2 and 2 where S1 and S2, the sample standard deviations, are estimates of sigma 1 and sigma 2, respectively, and sigma 1 and sigma 2 are the unknown population standard deviations. X1 and X2 are the sample means. Mu1 and Mu2 are the unknown population means. Letter 1d6ff equals the hypothesized differences between the two populations means. Substituting the sample variances of the two sample groups when the population's variances are unknown and the sample size is large, the t-distribution will provide good estimates using degrees of freedom. V equals letter 1d45b 1 plus n2 minus 2. Large in this case would be greater than 100 observations from the combined two groups, n1 plus n2, although other statisticians suggest that the definition of large is greater than 30 observations for each of the two groups. The number of degrees of freedom, df, requires a somewhat complicated calculation. The df are not always a whole number. The test statistic above is approximated by the student's t-distribution with df as follows. Degrees of freedom, the standard error is letter 1d460 1 2 and 1 plus, letter 1d460 2 2 and 2 2, 1 letter 1d45b 1 1 is letter 1d460 1 2 and 1 2 plus, 1 letter 1d45b 2 1 is letter 1d460 2 2 and 2 2 when both sample sizes n1 and n2 are 30 or larger. The student's t approximation is very good. If each sample has more than 30 observations, then the degrees of freedom can be calculated as letter 1d45b 1 plus letter 1d45b 2 minus 2. The format of the sampling distribution, differences in sample means, specifies that the format of the null and alternative hypothesis is the test hypothesis for differences between two means H0. Micro 1 minus micro 2 equals letter 1d6ff0 ha. Micro 1 minus micro 2 not equal to letter 1d6ff0, where delta 0 is the hypothesized difference between the two means. If the question is simply, is there any difference between the means, then delta 0 equals 0 and the null and alternative hypotheses becomes H0. Micro 1 equals micro 2 ha. Micro 1 not equal to micro 2, an example of when delta 0 might not be 0, is when the comparison of the two groups requires a specific difference for the decision to be meaningful. Imagine that you are making a capital investment. You are considering changing from your current model machine to another. You measure the productivity of your machines by the speed they produce the product. It may be that a contender to replace the old model is faster in terms of product throughput, but is also more expensive. The second machine may also have more maintenance costs, setup costs, etc. The null hypothesis would be set up so that the new machine would have to be better than the old one by enough to cover these extra costs in terms of speed and cost of production. This form of the null and alternative hypothesis shows how valuable this particular hypothesis test can be. For most of our work, we will be testing simple hypotheses asking if there is any difference between the two distribution means. Example 10. One independent group's the Kona Iki Corporation produces coconut milk. They take coconuts and extract the milk inside by drilling a hole and pouring the milk into a vat for processing. They have both a day shift called the B shift and a night shift called the G shift to do this part of the process. They would like to know if the day shift and the night shift are equally efficient in processing the coconuts. A study is done sampling 9 shifts of the G shift and 16 shifts of the B shift. The results of the number of hours required to process 100 pounds of coconuts is presented in Table 10. 1. A study is done and data are collected, resulting in the data in Table 10. One sample size average number of hours to process 100 pounds of coconuts, sample standard deviation G shift 920. 866 B shift 16321. Table 10. One problem is there a difference in the mean amount of time for each shift to process 100 pounds of coconuts. Test at the 5% level of significance. Solution: the population standard deviations are not known and cannot be assumed to equal each other. Let G be the subscript for the G shift and B be the subscript for the B shift. Then μ is the population mean for G shift and μ is the population mean for B shift. This is a test of two independent groups, two population means, random variable. X letter 1D454 minus XB equals difference in the sample mean amount of time between the G shift and the B shift takes to process the coconuts. H0 μg equals μb H0, μg equals ha, μg not equal to μb ha, μg not equal to the words the same tell you H0 has an equals. Since there are no other words to indicate ha is either faster or slower, this is a two-tailed test. Distribution for the test: use TDF where DF is calculated using the DF formula for independent groups, two population means above. Using a calculator, DF is approximately 18.8462. Graph: this is a normal distribution curve representing the difference in the average amount of time girls and boys play sports all day. The mean is equal to 0 and the values -1, 2, 0 and 1, 2 are labeled on the horizontal axis. Two vertical lines extend from -1, 2 and 1, 2 to the curve. The region to the left of x equals -1, 2 and the region to the right of x equals 1, 2 are shaded to represent the p-value. The area of each region is 0. 28, figure 10. 3tc equals x1 minus x2 minus letter 1 d6ff 0 square root s21 and 1 plus s22 and 2 equals -3. When we next find the critical value on the t-table using the degrees of freedom from above. The critical value 293 is found in the 25 column. This is alpha/2 at 19 degrees of freedom. The convention is to round up the degrees of freedom to make the conclusion more conservative. Next, we calculate the test statistic and mark this on the t-distribution graph. Make a decision. Since the calculated t-value is in the tail, we cannot accept the null hypothesis that there is no difference between the two groups. The means are different. The graph has included the sampling distribution of the differences in the sample means to show how the t-distribution aligns with the sampling distribution data. We see in the top panel that the calculated difference in the two means is 2, and the bottom panel shows that this is 3 standard deviations from the mean. Typically, we do not need to show the sampling distribution graph and can rely on the graph of the test statistic, the t-distribution in this case, to reach our conclusion. Conclusion. At the 5% level of significance, the sample data show there is sufficient evidence to conclude that the mean number of hours that the G shift takes to process 100 pounds of coconuts is different from the B shift. Mean number of hours for the B shift is greater than the mean number of hours for the G shift. Try at 10, 1, 2 samples are shown in table 10. 2. Both have normal distributions. The means for the two populations are thought to be the same. Is there a difference in the means? Test at the 5% level of significance. Sample size: sample mean, sample standard deviation population, a 2551 population B 164712 table 10. 2. Note: when the sum of the sample sizes is larger than 30, and 1 plus n2 30, you can use the normal distribution to approximate the student's t. Use the student's t distribution, however, whenever possible. Example 10. 2. A study is done to determine if Company A retains its workers longer than Company B. It is believed that Company A has a higher retention than Company B. The study finds that in a sample of 11 workers at Company A, their average time with the company is 4 years, with a standard deviation of 5 years. A sample of 9 workers at Company B finds that the average time with the company was 5 years with a standard deviation of 1 year. Test this proposition at the 1% level of significance. Problem A: is this a test of two means or two proportions? Solution: two means because time is a continuous random variable. Problem B: are the population's standard deviations known or unknown? Solution B: unknown. Problem C: which distribution do you use to perform the test? Solution C: students t. Problem D: what is the random variable? Solution D: x letter 1d434 minus xb. Problem E: what are the null and alternate hypotheses? Solution E: letter 1d43b O stroke. Letter 1d707 letter 1d434 less or equal to letter 1d707 letter 1d435 ha. Letter 1d707 letter 1d434 letter 1d707 letter 1d435. Problem F: is this test right, left, or two-tailed? Solution F: right one-tailed test. This is a normal distribution curve with mean equal to 0. A vertical line near the tail of the curve to the right of 0 extends from the axis to the curve. The region under the curve to the right of the line is shaded. Figure 10. 4. Problem G: what is the value of the test statistic? Solution TC equals x1 minus x2 minus letter 1d6ff 0 square root s21 and 1 plus s22 and 2 equals 0. 89 Problem H. Can you accept reject the null hypothesis? Solution H cannot reject the null hypothesis that there is no difference between the two groups. Test statistic is not in the tail. The critical value of the t-distribution is 2,764 with 10 degrees of freedom. This example shows how difficult it is to reject a null hypothesis with a very small sample. The critical values require very large test statistics to reach the tail. Problem I. Conclusion. Solution I. At the 1% level of significance, from the sample data, there is not sufficient evidence to conclude that the retention of workers at Company A is longer than Company B on average. Try it 10. 2. A study is done to determine if Company A retains its workers longer than Company B. Company A samples 15 workers, and their average time with the company is 5 years with a standard deviation of 1-2. Company B samples 20 workers, and their average time with the company is 4-5 years with a standard deviation of 0.8. The populations are normally distributed. Are the population standard deviations known? Conduct an appropriate hypothesis test. At the 5% significance level, what is your conclusion? Example 10. 3. Problem and interesting research question is the effect, if any, that different types of teaching formats have on the grade outcomes of students. To investigate this issue, one sample of students' grades was taken from a hybrid class and another sample taken from a standard lecture format class. Both classes were for the same subject. The mean course grade in percent for the 35 hybrid students is 74 with a standard deviation of 16. The mean grades of the 40 students form the standard lecture class was 76% with a standard deviation of 9. Test at 5% to see if there is any significant difference in the population mean grades between standard lecture course and hybrid class. Try at 10. 3. Two professors A and B teach classes on the same subjects. Scores of 10 students from each class are selected randomly. The final exam scores of the students are as follows. Professor A, 97, 62, 73, 58, 84, 74, 66, 93, 73, 85, Table 10. 3. Professor B, 85, 64, 74, 55, 76, 67, 72, 84, 71, 98, Table 10. 4. Professor A says that the mean score of their class is more than the mean of Professor B's class. Is Professor A correct? Test at a 5% significance level. Answer the following questions. Is this a test of two means or two proportions? Are the population standard deviations known or unknown? Which distribution do you use to perform the test? What is the random variable? What are the null and alternative hypotheses? Write the null and alternative hypotheses in words and in symbols. Is this test right, left, or two-tailed? What is the p-value? Do you reject or not reject the null hypothesis? At the level of significance from the sample data, there is not sufficient evidence to conclude that. Cohen's d is a measure of effect size based on the differences between two means. Cohen's d, named for United States statistician Jacob Cohen, measures the relative strength of the differences between the means of two populations based on sample data. The calculated value of effect size is then compared to Cohen's standards of small, medium, and large effect sizes. Size of effect d small 0, 2 medium 0, 5 large 0, 8 Table 10. 5. Cohen's standard effect sizes. Cohen's d is the measure of the difference between two means divided by the pooled standard deviation. X1, X2, letter 1 D460, letter 1 D45D, letter 1 D45C, letter 1 D45C, letter 1 D459, letter 1 D452, letter 1 D451. Where letter 1 D460, letter 1 D45D, letter 1 D45C, letter 1 D45C, letter 1 D459, letter 1 D452, letter 1 D451 equals square. Letter 1 D45B1, 1, letter 1 D460. 1 plus, letter 1 D45B2, 1, letter 1 D460, 2, 2, letter 1 D45B1 plus, letter 1 D45B2, 2. It is important to note that Cohen's d does not provide a level of confidence as to the magnitude of the size of the effect comparable to the other tests of hypothesis we have studied. The sizes of the effects are simply indicative. Example 10, 4 problem calculate Cohen's d for example 10. 2 is the size of the effect small, medium, or large. Explain what the size of the effect means for this problem. Solution x equals 4 s1 equals 1 5 and 1 equals 11, x2 equals 3 5 s2 equals 1 and 2 equals 9 d equals 0. 384 The effect is small because 0. 384 is between Cohen's value of 0.2 for small effect size and 0.5 for medium effect size. The size of the differences of the means for the two companies is small, indicating that there is not a significant difference between them. Try at 10. 4 Calculate Cohen's d for try at 10. 4. Is the size of the effect small, medium, or large? Explain what the size of the effect means for this problem. Typically, we can never expect to know any of the population parameters, mean, proportion, or standard deviation. When testing hypotheses concerning differences in means, we are faced with the difficulty of two unknown variances that play a critical role in the test statistic. We have been substituting the sample variances just as we did when testing hypotheses for a single mean. And as we did before, we used a student's t to compensate for this lack of information on the population variance. There may be situations, however, when we do not know the population variances, but we can assume that the two populations have the same variance. If this is true, then the pooled sample variance will be smaller than the individual sample variances. This will give more precise estimates and reduce the probability of discarding a good null. The null and alternative hypotheses remain the same, but the test statistic changes too. Letter 1D461 letter 1D450 equals x1 minus x2 minus letter 1D6FF0 square root letter 1D4462p 1 and 1 plus 1 and 2, where letter 1D4462p is the pooled variance given by the formula. S2 letter 1D45d equals letter 1D45b1 minus 1, letter 1D46021 1 plus, letter 1D45b2 minus 1, letter 1D46022, letter 1D45b1 plus letter 1D45b2 minus 2. Example 10. 5 problem: a drug trial is attempted using a real drug and a pill made of just sugar. 18 people are given the real drug in hopes of increasing the production of endorphins. The increase in endorphins is found to be on average 8 micrograms per person, and the sample's standard deviation is 4 micrograms. 11 people are given the sugar pill, and their average endorphin increase is 4 micrograms with a standard deviation of 2. 4. From previous research on endorphins, it is determined that it can be assumed that the variances within the two samples can be assumed to be the same. Test at 5% to see if the population mean for the real drug had a significantly greater impact on the endorphins than the population mean with the sugar pill. Solution: first, we begin by designating one of the two groups Group 1 and the other Group 2. This will be needed to keep track of the null and alternative hypotheses. Let's set Group 1 as those who received the actual new medicine being tested, and therefore Group 2 as those who received the sugar pill. We can now set up the null and alternative hypothesis as H0. Micro 1 less or equal to micro 2 H1. Micro 1 micro 2, this is set up as a one-tailed test with the claim in the alternative hypothesis that the medicine will produce more endorphins than the sugar pill. We now calculate the test statistic, which requires us to calculate the pooled variance. Letter 1D4462p using the formula above. Letter 1D461 letter 1D450 equals x1 minus x2 minus letter 1D6FF0 square root letter 1D4462p 1 and 1 plus 1 and 2 equals 8 minus 4 minus 0 square root 20. 4933 118 plus 111 equals 2. 31 T alpha allows us to compare the test statistic and the critical value. Letter 1D461 letter 1D6FC equals 1. 703 a T letter 1D451 letter 1D453 equals letter 1D45B1 plus letter 1D45B2 minus 2 equals 18 plus 11 minus 2 equals 27. The test statistic is clearly in the tail 2. 31 is larger than the critical value of 1. 703, and therefore we cannot maintain the null hypothesis. Thus, we conclude that there is significant evidence at the 95% level of confidence that the new medicine produces the effect desired. Try at 10. 5 weighted alpha is a measure of risk-adjusted performance of stocks over a period of a year. A high positive weighted alpha signifies a stock whose price has risen, while a small positive weighted alpha indicates an unchanged stock price during the time period. Weighted alpha is used to identify companies with strong upward or downward trends. The weighted alpha for the top 30 stocks of banks in the Northeast and in the West, as identified by Nasdaq on May 24, 2013, are listed in Table 10.6 and Table 10.7, respectively. 94, 275, 269, 652, 048, 041, 936, 433, 431, 527. 677, 371, 967, 556, 46, 238, 435, 233, 028, 726, 576, 371. 756, 348, 743, 237, 633, 731, 828, 526, Table 10, 6 Northeast 126, 070. 665, 251, 445, 537, 033, 029, 623, 722, 6 116, 170, 658, 251. 243, 236, 031, 428, 723, 521, 678, 268, 255, 650, 339, 034, 131. 025, 323, 421, 5 Table 10, 7 West. Is there a difference in the weighted alpha of the top 30 stocks of banks in the Northeast and in the West? Test at a 5% significance level. Answer the following questions. Is this a test of two means or two proportions? Are the population standard deviations known or unknown? Which distribution do you use to perform the test? What is the random variable? What are the null and alternative hypotheses? Write the null and alternative hypotheses in words and in symbols. Is this test right, left, or two-tailed? What is the p-value? Do you reject or not reject the null hypothesis? At the level of significance from the sample data, there is not sufficient evidence to conclude that. Calculate Cohen's d and interpret it. Proportions have their base in the binomial probability distribution. As a probability distribution, we know the mean and standard deviation of the distribution. As a binary or categorical sample data set, we lose this knowledge from when we knew the population parameters. We do not know the population mean, micro equals letter 1d45b letter 1d45d, or variance. Letter 1d70e equals letter 1d45b letter 1d45d letter 1d45e. We can gather data that we know comes from a binary distribution but not know the specific parameter. It is then that we have moved from probability to inferential statistics. When conducting a hypothesis test that compares two independent population proportions, the following characteristics should be present. The two independent samples are random samples that are independent. The number of successes is at least 5, and the number of failures is at least 5 for each of the samples. Growing literature states that the population must be at least 10 or even perhaps 20 times the size of the sample. This keeps each population from being oversampled and causing biased results. Comparing two proportions like comparing two means is common. If two estimated proportions are different, it may be due to a difference in the populations, or it may be due to chance in the sampling. A hypothesis test can help determine if a difference in the estimated proportions reflects a difference in the two population proportions. Like the case of differences in sample means, we construct a sampling distribution for differences in sample proportions. Letter 1d45d A minus letter 1d45d B, where p letter 1d434 equals xa, and p letter 1d435 equals nb are the sample proportions for the two sets of data in question. xa and xb are the number of successes in each sample group respectively, and na and nb are the respective sample sizes from the two groups. Again, we go the central limit theorem to find the distribution of this sampling distribution for the differences in sample proportions. And again, we find that this sampling distribution, like the ones past, are normally distributed as proved by the central limit theorem, as seen in Figure 10. 5. Figure 10. 5. Generally, the null hypothesis allows for the test of a difference of a particular value, letter 1 d6ff0, just as we did for the case of differences in means. h0. Letter 1 d45d1 minus letter 1 d45d2 equals letter 1 d6ff0 h1. Letter 1d45d1 minus letter 1d45d2 not equal to letter 1d6ff0. Most common, however, is the test that the two proportions are the same. That is h0 aha. Letter 1d45d a not equal to letter 1d45d letter 1d435 to conduct the test. We use a pooled proportion PC. The pooled proportion is calculated as follows. Letter 1d45d letter 1d450 equals NA plus NB. The test statistic z-score is letter 1d440 letter 1d450 equals letter 1d45d letter 1d434 minus letter 1d45d letter 1d435 minus letter 1d6ff0 square root letter 1d450 letter 1d450 1 minus letter 1d45d letter 1d450 1 plus 1 NB, where delta 0 is the hypothesized differences between the two proportions and PC is the pooled variance from the formula above. Example 10. 6 problem. A bank has recently acquired a new branch and thus has customers in this new territory. They are interested in the default rate in their new territory. They wish to test the hypothesis that the default rate is different from their current customer base. They sampled 200 files in Area A, their current customers, and find that 20 have defaulted. In Area B, the new customers, another sample of 200 files shows 12 have defaulted on their loans. At a 10% level of significance, can we say that the default rates are the same or different? Solution: this is a test of proportions. We know this because the underlying random variable is binary, default or not default. Further, we know it is a test of differences in proportions because we have two sample groups, the current customer base and the newly acquired customer base. Let A and B be the subscripts for the two customer groups. Then PA and PB are the two population proportions we wish to test. Random variable PA/PB equals difference in the proportions of customers who defaulted in the two groups. H0, PA equals letter 1d45d letter 1d435 ha. PA not equal to letter 1d45d letter 1d435. The words is a difference tell you the test is two-tailed. Distribution for the test. Since this is a test of two binomial population proportions, the distribution is normal. Letter 1D45D letter 1D450 equals XA plus XBNA plus NB equals 20 plus 12 200 plus 200 equals 0. 081 letter 1D45D letter 1D450 equals 0. 92 PA PB equals 0. 4 follows an approximate normal distribution. Estimated proportion for group A. Letter 1D45D equals XANA equals 2200 equals 0. 1 estimated proportion for group B. Letter 1D45D equals XBNB equals 12200 equals 0. 6. The estimated difference between the two groups is PA PB equals 0. 106 equals 0.4. Normal distribution curve of the difference in the percentages of adult patients who don't react to medication A and B after 30 minutes. The mean is equal to 0 and the values 4, 0 and 0.4 are labeled on the horizontal axis. Two vertical lines extend from -0, 4 and 0. 4 to the curve, the region to the left of -0, 4 and the region to the right of 0. 4 are each shaded to represent 1/2 p-value equals 0. 702. Figure 10, 6 letter 1D440 letter 1D450 equals P minus letter 1D6FF0 square root letter 1D443 letter 1D450. 1 minus letter 1D443 letter 1D450. 1 NA plus 1 NB equals 1. 47. The calculated test statistic is 147 and is not in the tail of the distribution. Make a decision. Since the calculate test statistic is not in the tail of the distribution, we cannot reject H0. Conclusion: at a 1% level of significance from the sample data, there is not sufficient evidence to conclude that there is a difference between the proportions of customers who defaulted in the two groups. Try at 10. 6. Two types of valves are being tested to determine if there is a difference in pressure tolerances. 15 out of a random sample of 100 of valve, a cracked under 4,500 psi. 6 out of a random sample of 100 of valve B cracked under 4,500 psi. Test at a 5% level of significance. Even though this situation is not likely, knowing the population standard deviations is very unlikely, the following example illustrates hypothesis testing for independent means with known population standard deviations. The sampling distribution for the difference between the means is normal in accordance with the central limit theorem. The random variable is x1, x2. The normal distribution has the following format. The standard deviation is square root letter 1D70E12N1 plus letter 1D70E22N2. The test statistic z-score is letter 1D440 letter 1D450 equals x1, x2 letter 1D6FF0 square root letter 1D70E12N1 plus letter 1D70E22N2. Example 10. 7 independent groups, population standard deviations known. The mean lasting time of 2 competing floor waxes is to be compared. 20 floors are randomly assigned to test each wax. Both populations have a normal distributions. The data are recorded in Table 10. 8. Wax sample mean number of months floor wax last population standard deviation 130, 322. 90, 36 Table 10. 8. Problem: does the data indicate that wax 1 is more effective than wax 2? Test at a 5% level of significance. Solution: this is a test of 2 independent groups, 2 population means, population standard deviations known. Random variable x1, x2 equals difference in the mean number of months the competing floor waxes last. H0, letter 1D7071 less or equal to letter 1D7072 ha. Letter 1D7071, letter 1D7072. The words is more effective says that wax 1 lasts longer than wax 2 on average. Longer is a symbol and goes into ha. Therefore, this is a right-tailed test. Distribution for the test. The population standard deviations are known, so the distribution is normal. Using the formula for the test statistic, we find the calculated value for the problem. Letter 1D440 letter 1D450 equals letter 1D7071 minus letter 1D7072 minus letter 1D6FF0 square root letter 1D70E21N1 plus letter 1D70E22N2 equals 0. 1. This is a normal distribution curve with mean equal to 0. The values 0 and 0,1 are labeled on the horizontal axis. A vertical line extends from 0,1 to the curve. The region under the curve to the right of the line is shaded to represent p-value equals 0.1799. Figure 10. 7. The estimated difference between E2 means is x1, x2 equals 329 equals 0. 1. Compare calculated value and critical value in z-alpha. We mark the calculated value on the graph and find the calculated value is not in the tail, therefore we cannot reject the null hypothesis. Make a decision: the calculated value of the test statistic is not in the tail, therefore you cannot reject H0. Conclusion: At the 5% level of significance from the sample data, there is not sufficient evidence to conclude that the mean time wax 1 lasts is longer. Wax 1 is more effective than the mean time wax 2 lasts. Try at 10. 7. The means of the number of revolutions per minute of two competing engines are to be compared. 30 engines of each type are randomly assigned to be tested. Both populations have normal distributions. Table 10. 9 shows the result. Do the data indicate that engine 2 has higher RPM than engine 1? Test at a 5% level of significance. Engine sample mean number of RPM population standard deviation 1 1552 1660 Table 10. 9 Example 10. 8. An interested citizen wanted to know if Democratic U.S. senators are older than Republican U.S. senators on average. On May 26, 2013, the mean age of 30 randomly selected Republican senators was 61 years 247 days old, 61. 675 years, with a standard deviation of 1017 years. The mean age of 30 randomly selected Democratic senators was 61 years 257 days old, 61. 704 years, with a standard deviation of 55 years. Problem: do the data indicate that Democratic senators are older than Republican senators on average? Test at a 5% level of significance. Solution: this is a test of two independent groups, two population means. The population standard deviations are unknown, but the sum of the sample sizes is 30 plus 30 equals 60, which is greater than 30, so we can use the normal approximation to the student's distribution. Subscripts 1. Democratic senators. 2. Republican senators. Random variable. X1, X2 equals difference in the mean age of Democratic and Republican U.S. senators. H0, letter 1 D7071 1 less or equal to letter 1 D7072 H0. Letter 1 D7071 minus letter 1 D7072 less or equal to 0 ha. Letter 1 D7071 letter 1 D7072 ha. Letter 1 D7071 minus letter 1 D7072. The words older than translates as a symbol and goes into ha. Therefore, this is a right-tailed test. This is a normal distribution curve with mean equal to 0. A vertical line to the right of 0 extends from the axis to the curve. The region under the curve to the right of the line is shaded, representing p-value equals 0.4955. Figure 10. 8. Make a decision. The p-value is larger than 5%, therefore we cannot reject the null hypothesis. By calculating the test statistic, we would find that the test statistic does not fall in the tail, therefore we cannot reject the null hypothesis. We reach the same conclusion using either method of making this statistical decision. Conclusion: at the 5% level of significance from the sample data, there is not sufficient evidence to conclude that the mean age of Democratic senators is greater than the mean age of the Republican senators. Try at 10. 8. The average age of 10 professors selected randomly in University A is 46. 672 with a standard deviation of 53. The average age of 10 professors selected randomly in University B is 47. 531 with a standard deviation of 783. Does the data indicate that University A has older professors than University B on average? Test at a 5% level of significance. In most cases of economic or business data, we have little or no control over the process of how the data are gathered. In this sense, the data are not the result of a planned, controlled experiment. In some cases, however, we can develop data that are part of a controlled experiment. This situation occurs frequently in quality control situations. Imagine that the production rates of two machines built to the same design, but at different manufacturing plants, are being tested for differences in some production metrics such as speed of output or meeting some production specifications such as strength of the product. The test is the same in format to what we have been testing, but here we can have match pairs for which we can test if differences exist. Each observation has its match pair against which differences are calculated. First, the differences in the metric to be tested between the two lists of observations must be calculated, and this is typically labeled with the letter D. Then, the average of these matched differences, xd equals some sign letter 1d4651 minus letter 1d4652, n is calculated as is its standard deviation sd. We expect that the standard deviation of the differences of the matched pairs will be smaller than unmatched pairs, because presumably fewer differences should exist because of the correlation between the two groups. When using a hypothesis test for matched or paired samples, the following characteristics may be present. Simple random sampling is used. Sample sizes are often small. Two measurement samples are drawn from the same pair of individuals or objects. Differences are calculated from the matched or paired samples. The differences from the sample that is used for the hypothesis test. Either the matched pairs have differences that come from a population that is normal, or the number of differences is sufficiently large so that distribution of the sample mean of differences is approximately normal, as has been the case using the central limit theorem. In a hypothesis test for matched or paired samples, subjects are matched in pairs and differences are calculated. The differences are the data. The population mean for the differences μ is then tested using a student's t-test for a single population mean with n 1 degrees of freedom, where n is the number of differences, that is, the number of pairs not the number of observations. The null and alternative hypotheses for this test are H0, microletter 1 D451 not equal to 0. The test statistic is letter 1 D461 letter 1 D450 equals x letter 1 D451 minus letter 1 D707 letter 1 D451, letter 1 D460 letter 1 D451 square root letter 1 D45b, example 10. 9 problem. A company has developed a training program for its entering employees because management has become concerned with the results of the 6-month employee review. They hope that the training program can result in better 6-month reviews. Each trainee constitutes a pair, the entering score the employee received when first entering the firm and the score given at the 6-month review. The difference in the two scores were calculated for each employee, and the means for before and after the training program was calculated. The sample mean before the training program was 20.4 and the sample mean after the training program was 23.9. The standard deviation of the differences in the two scores across the 20 employees was 3.8 points. Test at the 10% significance level the null hypothesis that the two population means are equal against the alternative, that the training program helps improve the employees' scores. Solution. The first step is to identify this as a two-sample case, before the training and after the training. This differentiates this problem from simple one-sample issues. Second, we determine that the two samples are paired. Each observation in the first sample has a paired observation in the second sample. This information tells us that the null and alternative hypotheses should be H0. Microletter 1 D451 less or equal to 0 Microletter 1 D4510, 0. This form reflects the implied claim that the training course improves scores. The test is one-tailed and the claim is in the alternative hypothesis. Because the experiment was conducted as a matched paired sample rather than simply taking scores from people who took the training course those who didn't, we use the matched pair test statistic. Test statistic, letter 1 D461 letter 1 D450 equals x letter 1 D451 minus microletter 1 D451, letter 1 D446 letter 1 D451 square root letter 1 D45b equals 23. 9 minus 20, 4 minus 0, 3 8 square root 20 equals 4. 12. In order to solve this equation, the individual scores, pre-training course and post-training course, need to be used to calculate the individual differences. These scores are then averaged and the average difference is calculated. X letter 1 D451 equals sum sign, letter 1 D465 1 minus letter 1 D465 2. And from these differences, we can calculate the standard deviation across the individual differences. Letter 1 D446 letter 1 D451 equals square root square root square root square root square root sum sign. Letter 1 D451 letter 1 D456 minus x letter 1 D451 2 letter 1 D45b minus 1 letter 1 D464 letter 210 e letter 1 D452 letter 1 D45f letter 1 D45. Letter 1 D451 letter 1 D456 equals letter 1 D465 1 letter 1 D456 minus letter 1 D465 2I. We can now compare the calculated value of the test statistic. For 12 with the critical value. The critical value is a student's t with degrees of freedom equal to the number of pairs, not observations, minus 1. In this case 20 pairs and at 90% confidence level Ta2 equals plus or minus 1. 729 at df equals 21 equals 19. The calculated test statistic is most certainly in the tail of the distribution, and thus we cannot accept the null hypothesis that there is no difference from the training program. Evidence seems indicate that the training aids employees in gaining higher scores. Try at 10. 9-5 ball players think they can throw the same distance with their dominant hand throwing and offhand catching hand. The data were collected and recorded in Table 10. 10. Conduct a hypothesis test to determine whether the mean difference in distances between the dominant and offhand is significant. Test at the 5% level. Player 1, player 2, player 3, player 4, player 5 dominant hand, 120, 111, 135, 140, 125. Offhand 105, 109, 98, 111, 99. Table 10. 10. Example 10. 10 problem. A study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown in Table 10. 11. A lower score indicates less pain. The before value is matched to an after value and the differences are calculated. Are the sensory measurements on average lower after hypnotism? Test at a 5% significance level. Subject. A B C D E F G H before 6, 6 6, 5 9 0 10 3 11 3 8 1 6 3 11 6 after 6 8 2 4 7 4 8 5 8 1 6 1 3 4 2. Table 10, 11 solution corresponding before and after values form matched pairs. Calculate after, before. After data before data difference 6866022, 465 minus 4. 1749 minus 1, 68, 510, 3 minus 1, 88, 111, 3 minus 3, 2618, 1 minus 2, 3, 4, 6, 3 minus 2, 9, 2, 11, 6 minus 9, 6 table 10. 12 the data for the test are the differences 0. 2 4 1 1 6 1 8 3 2 2 2 9 9 6. The sample mean and sample standard deviation of the differences are XD equals 313 and letter 1D 460 letter 1D 451 equals 2. 91. Verify these values. Let letter 1D 707 letter 1D 451 be the population mean for the differences. We use the subscript D to denote differences. Random variable. XD equals the mean difference of the sensory measurements H0. Mewed greater or equal to 0, the null hypothesis is 0 or positive, meaning that there is the same or more pain felt after hypnotism. That means the subject shows no improvement. Mewed is the population mean of the differences. Mewed the alternative hypothesis is negative, meaning there is less pain felt after hypnotism. That means the subject shows improvement. The score should be lower after hypnotism, so the difference ought to be negative to indicate improvement. Distribution for the test. The distribution is a student's T with DF equals N, 1 equals 8, 1 equals 7. Use T7. Notice that the test is for a single population mean. Calculate the test statistic and look up the critical value using the student's T distribution. The calculated value of the test statistic is 3.6, and the critical value of the T distribution with 7 degrees of freedom at the 5% level of confidence is 1. 895 with a one-tailed test. Normal distribution curve of the average difference of sensory measurements with values of minus 313 and 0. A vertical upward line extends from 13 to the curve and the p-value is indicated in the area to the left of this value. Figure 10.9, XD is the random variable for the differences. The sample mean and sample standard deviation of the differences are XD equals 313, SD equals 2. 91. Compare the critical value for alpha against the calculated test statistic. The conclusion from using the comparison of the calculated test statistic and the critical value will gives us the result. In this question, the calculated test statistic is 3.6 and the critical value is 1,895. The test statistic is clearly in the tail, and thus we cannot accept the null hypotheses that there is no difference between the two situations, hypnotized and not hypnotized. Make a decision cannot accept the null hypothesis H0. This means that mewed 0 and there is a statistically significant improvement. Conclusion. At a 5% level of significance from the sample data, there is sufficient evidence to conclude that the sensory measurements on average are lower after hypnotism. Hypnotism appears to be effective in reducing pain. Try it 10. 10. A study was conducted to investigate how effective a new diet was in lowering cholesterol. Results for the randomly selected subjects are shown in the table. The differences have a normal distribution. Are the subjects' cholesterol levels lower on average after the diet? Test at the 5% level. Subject A, B, C, D, E, F, G, H. I before 209, 210, 205, 198, 216, 217, 238, 240, 222. After 199, 207, 189, 209, 217, 202, 211, 223, 201. Table 10. 13. Example 10. 11. A college softball coach was interested in whether the college's strength development class increased their players' maximum lift in pounds. 4 players were asked to participate in the study. The amount of weight they could each lift was recorded before they took the strength development class. After completing the class, the amount of weight they could each lift was again measured. The data are as follows. Weight in pounds, player 1, player 2, player 3, player 4. Amount of weight lifted prior to the class 205, 241, 338, 368. Amount of weight lifted after the class 295, 252, 330, 360. Table 10. 14. The coach wants to know if the strength development class makes the players stronger on average. Record the differences data. Calculate the differences by subtracting the amount of weight lifted prior to the class from the weight lifted after completing the class. The data for the differences are 90, 11, minus 8, minus 8. XD equals 21, 3, SD equals 46. 7. Using the difference data, this becomes a test of a single mean. Define the random variable, XD mean difference in the maximum lift per player. The distribution for the hypothesis test is a student's t with 3 degrees of freedom. H0, μ less or equal to 0, μ normal distribution curve with values of 0 and 21, 3. A vertical upward line extends from 21, 3 to the curve, and the p-value is indicated in the area to the right of this value. Figure 10. 10. Calculate the test statistic. Look up the critical value. The calculated value of the test statistic is 0.91. The critical value of the student's t at 5% level of significance and 3 degrees of freedom is 2,353. Decision. If the level of significance is 5%, we cannot reject the null hypothesis because the calculated value of the test statistic is not in the tail. What is the conclusion? At a 5% level of significance, from the sample data, there is not sufficient evidence to conclude that the strength development class helped to make the players stronger on average. Be sure to note in your conclusion that a sample size of only 4 leaves a degree of freedom of only 3 and sets the critical value very large. In short, sample size so small cannot result in always meaningful conclusions. Try at 10, 11. A new prep class was designed to improve SAT test scores. 4 students were selected at random. Their scores on 2 practice exams were recorded, one before the class and one after. The data recorded in Table 10, 15 are the scores on average higher after the class test at a 5% level. SAT scores student 1, student 2, student 3, student 4 score before class 1840, 1960, 1920, 21, 50 score after class 1920, 21, 60, 20, 220, 100. Table 10. 15.